Hello and welcome to the second lecture in our course in organic chemistry. I am Dr. Gor Sarkisian. We have begun the lecture with introduction of atomic structures. We went over some of the principles of quantum mechanics, and we have introduced the concept of atomic shells, subshells, and orbitals. Today, we will pick up by introducing other quantum values such as electron spins, nodes, radial variations of atomic orbitals, radial distribution functions, and so on. In addition to the three quantum numbers that we have already introduced in our previous lecture, we need to introduce a couple more to be able to completely describe the state of an atom. And today we will begin with talking about electron spin. Electron spin, quantum numbers related to the angular momentum of an electron. Angular momentum, have to be careful about this term because it is, in this particular context, it is a quantum number. And it's not really, one has to be careful not to think about it as a motion of a planet, for example. So, the spin is described with two atomic numbers, S and ms. S in this case is restricted to 1/2 for an electron. The magnitude of S is basically this term right here. Let's rewrite this. And obviously you should remember that this is the same as Planck's constant over 2 pi, because we're talking about angular momentums here. So the other number is ms, which is the spin magnetic quantum number, which can either be positive 1/2 or negative 1/2, or otherwise known as anti-clockwise spin or clockwise spin, denoted with arrow up or arrow down. So to be able to completely characterize the state of an atom, we need to have these 4 parameters, 3 of which were introduced in a previous lecture, the N, L, and M. If you do not remember, please go back and revisit. And we also need the ms. So for our model atom, which is hydrogenic atoms, these 4 parameters are what we need to describe the state of the atom. Another concept to introduce before moving forward are nodes. So the potential energy of an electron around its nucleus is spherically symmetrical and is proportional to the charge over radius. In this context, the orbitals are best expressed in terms of spherical polar coordinates, in which r here is the radius, and theta and phi are the azimuth. Just standard spherical coordinates. So if we look at it from this perspective, our wave function as a function of n, L, and ml have basically radial variation and angular variation. And if we look at it from this perspective, it is obvious that there are areas or positions, I should say, in which the wavefront passes through zero, right? It's either this component or this component are equal to zero. So from again this expression, it is quite obvious to see that there are two components here. The radial node occurs when the radial component, right, the radial component of the wave function passes through zero, and we have the angular node in which we have the angular component passing through zero. Now, as we will see, the numbers of both types of nodes increase with increasing energy as it relates to the quantum numbers n and l. Now let's take a closer look at the radial variations of atomic orbitals. Now let's consider the orbital 1s. 1s, as you remember, has a wave function of n equals 1, L is 0, and ml is also 0. Now, it decays exponentially from the nucleus, so do all the others, maybe at different rates, but the most important thing here is that S1 never passes through 0. However, not all orbitals behave this way. Some actually do go through 0, and before they begin their final oscillation, decay, shall we say. Now, if we want to express this mathematically, the relationship is as follows. So let's say we have an orbital with quantum number n and of course L, right? So the number of nodes would be n minus L minus 1. That's how many nodes it would have. So an orbital 2s has one orbital node. It's right here. Why? Because n is 2, and we have 2 minus 0 minus 1, right? L is 0. The next example of 3s orbital, we have n equals 3, which means we have 2 radial nodes. So the other orbitals, such as 2p orbitals, well, all of them pass through 0 at the nucleus. Remember this this form. S, on the other hand, is round. It has presence at the nucleus. So the important thing here is to remember for any series of the same type of orbitals, the first occurrence has no radial node. But second has one, third has two, and so on and so forth. Now let's try an example. Take a look at this. So here's a simple question. How many radial nodes do 3p, 3d, and 4f orbitals have? Now we need to remember the most basic. This is L minus 1, so N minus L minus 1. That's how we determine the our nodes. So 3p, if we remember, it has an N that is equal to 3 and L that is equal to 1. So therefore the radial nodes 3 minus 1, 3 minus L minus 1. 1. It has one radial node in which the wave function is 0. The 3D, N equals 3, L equals 2. Therefore, we have 0 radial nodes. Same thing is for 4F. 4F, N equals 4, L equals 3, therefore 0 radial nodes. Okay? So, the 3D and 4F orbitals are the first occurrence of the D and F orbitals, right? Which is indicative that there will be no radial nodes. So remember that. That's very important. The first occurrence of the orbital has no radial nodes. So, having said that, here is a question. Please respond to it and send it to me. How many radial orbitals does 5s orbital have? Before we move forward to radial distribution functions, here is another image that represents quite well how these radial distribution functions look like. Our S1, 1s, as we stated, has no radial nodes, and as you can see, no radial nodes. Our 2s has one radial node. Our 3s has two radial nodes. I really like this representation. This is the radial distribution function. It comes in handy to know the probability of finding an electron at a given distance from the nucleus. This can enable us to calculate basically the Coulombic forces that bind the electron to the nucleus. And in order to do this, we basically need to take the total probability of finding an electron at a particular radius around the nucleus in a sphere that encompasses the nucleus at the radius r, which has obviously a thickness of delta r, and integrate it all over the angles. I'm not going to go in depth into the integration. I'm sure you are well familiar with integrating over the square. Easy. This results in the function that we have here, the PR r squared times a function of r over r squared. Now this is basically for let's say for an s orbital, it comes out to be 4 pi r squared phi squared. Okay, and this is a r phi from previous slides. So what does this give us? Well, if we know the value of p at some radius r, we can state basically the probability of finding that electron somewhere in that shell, simply by multiplying p by dr, and of course we have some space there. Now let's look at this for an s1 orbital, and this is our expression for s1, and we have stated that the wave function decreases exponentially as the radius or the distance of the electron from the nucleus increases. In our case, this is the r squared. R squared increases, our wave function decreases. Therefore, there is a value of r in which it goes through a maximum. What does this mean? Well, it is the probability, right? So there is a certain distance in which the probability of finding the electron there is at its greatest. So in general, if, let's say, the charge of the nucleus increases, obviously the distance, this distance of finding the electron or increase of maximum of probability is decreasing. It's well, nucleus attracts the electron stronger, therefore closer. So we can therefore represent as R max being equal to alpha 0 divided by z. Okay, and alpha 0 is our Bohr's. Now we're not going to go into the details of it, but if you'd like to know, Bohr's radius, or alpha 0, is alpha 0 equals eta 0 squared divided by pi me e squared. So for the model of the atom that we have, alpha 0 is 52.9 picometers. So this is the number. Next comes the angular variation of atomic orbitals. All this is a description of atomic orbital shape. As we know very well, an orbital S has a spherical symmetrical shape. Basically, it has the same amplitude at a given distance from the nucleus. That distance, that spherical sphere around the nucleus, creates what's known as boundary surface. The boundary surface is the distance from the nucleus in which we have 90% probability of finding the electron there. With planes in which we have the angular wave function actually passing through zero are called an angular node and angular planes, as we have already discussed. And electron will not be found there. So here's a general, in general, an orbital with a quantum number L will have L nodal planes. In S orbital, the L is 0, therefore no nodal planes, and the boundary space of an S orbital is spherical. In cases in which the nodal plane cuts through the nucleus, we have separate regions of positive and negative wave functions. This is the most common graphical representation of boundary surface of a p orbital. Remember the standard infinity sign. The given shell are identically apart from the surface of their axis, and they lie in parallel in 3 different Cartesian centers of the nucleus, and each has the nodal plane passing through the nucleus. So basically we have one in X, we have one in Y, we have one in Z. X, Y, Z, Cartesian coordinates. The shading here, the dark and light brown, I suppose, simply represent the positive and negative amplitudes of the function. That's all, it's just a graphical representation. So here is the graphical representation of the lobes of d orbital. One of them, the dz2, looks different than others, but we will discuss why. So we are familiar with these. These are our standards: dx, dzx, dyz, and dxy. Right? And we can have 6 axes here. If you imagine it, we can move this around to have 6. However, we know that d orbital is constricted to only 5 orbitals. So as a result, we have this obscure looking orbital, which is nothing but a superimposition of the remaining orbitals to satisfy the constraints of 5 orbitals. Again, this is a graphical representation. We have to be able to visually see this. In reality, obviously, it doesn't look like this. And here is the graphical representation of the F orbital. Very similar in terms of representation of the d orbital. The only thing here that is visually more accessible is, well, this, for example, is quite simple. We put 8 balloons next to each other and they will form this. However, what I very much like and how it's represented here is this. You can clearly see how these are different from one another. Same thing stands true with this. So this is a very, very good graphical representation, but we also have this obscure combination here. And this is also because of the constraints of number of orbitals that we can have in F orbital, number of configurations. Now, question. In D, we have 5. How many do we have in F? So we will conclude with a quick remark about many electron atoms. Thus far, we've been talking about our modeled atom of hydrogen. Why? Because it has a single electron. But when we start talking about atoms with more than one electron, let's take the simplest one, helium. Well, it has only 2. But it is a many electron atom. So what happens here? Why does it get complicated? It's because now we have an n electrons, and we have to calculate the function of the 3n coordinates for all electrons. It becomes increasingly more challenging to exactly calculate this complex function. But it is possible to do numerical computations using software, because it's Schrodinger's equations. With computational power, it's a plug and play basically. But for practical purposes, for inorganic chemistry, we do use a lot of orbital approximations, in which the electron occupies an atomic orbital that resemble that of hydrogen atom. So we say that an electron occupies an atomic orbital. When we say that, we talk about the distribution of the corresponding wave function at a set quantum number. So that's food for thought. We will pick up next lecture with penetration and shielding. And this is it for today. Thank you for your attention.